because it indicates that you're interested in the seminars we're giving, and Australia and Griffith University. I'll give a little bit about my background first, okay? As an undergraduate, I studied geology, which of course means I have an interest in mining, because I only did 1 year geology, but it was very important. And then I did biology, botany and zoology. And then for my PhD, I did marine biology, but I did it in the Caribbean. I did it in Jamaica. And then in Australia, first I worked on the Great Barrier Reef, which is one of the largest coral reefs in the world. And for a number of years, I worked as environmental consultant, assessing impacts of mining, of agriculture, of coastal developments on the environment. So I was interested in biodiversity issues, water quality issues, rehabilitation issues, contaminated soils, and in an applied sense. Then I went to Griffith University, and that was 20 years ago now. As Gia mentioned, one of the most important disciplines of Griffith University is the environment. We were the first university to offer interdisciplinary environmental science, and that was in '75, and we were the first. And that meant that in interdisciplinary environmental science, we not only had biologists and ecologists, but we also had chemists, soil scientists, hydrologists, geologists, engineers, mathematicians, sociologists, economists, health people. So it was very integrated, all those disciplines from when we first started. Then, in 1990, it was decided to have environmental engineering. In other words, we wanted to apply our expertise and knowledge on the environment to addressing what we perceived problems may be associated with engineering. So we wanted to look at minimizing air pollution, minimizing waste, both municipal solid waste, garbage, minimizing sewage waste, looking at remediating the soils, remediating, as I say, mine sites. So we developed environmental engineering, and that was 21 years ago. And Griffith University was the first university in Australia to have environmental engineering. So we were the first to have environmental science in '75, and the first then to have environmental engineering. And I am in the School of Engineering, but in specialty in environmental engineering. Now, as mentioned to you, my background was obviously ecology, biology, a bit of geology. However, I work with engineers, I teach engineers. But my focus is what I call ecotechnologies. So as an ecologist, I'm interested in phytoremediation. That's using plants to remediate water, to remediate soils, to remediate landfills. Also bioremediation using microorganisms. So that's my specific area. And so I teach my engineers about environmental microbiology. I teach them a bit about ecology. and also from me they learn a little bit about soils, but also wetlands. So today I'm now going to actually give you an overview of my research area, also demonstrating the interdisciplinarity of that. And the topic, as you can see, is I'm looking at constructed wetlands, engineered wetlands for treating municipal wastewater, sewage, but also stormwater. We treat a lot of stormwater, as you'll see. That's more important now. But I also want to focus on why they're important. I want to talk about the ecological, social and economic values of integrating these constructed wetlands. So I will now start my presentation. I want to make sure that's okay. So first of all, I'm going to give you a little bit of an overview. I'm going to set the context of the issues of water in Australia. I'm then going to describe the different types of constructed engineered wetlands. I'm then going to talk about their ecological importance, water treatment processes that are carried out within the wetlands, a little bit about design of wetlands in order to maximise the removal of contaminants, and finally an overview that will take into account the social and economic values. Well, I'm well aware that Brazil has the largest wetland in the world, your Amazon system. But I'm sure, as you also know, unfortunately a lot of wetlands in the world, including Amazon, are being destroyed. Many cities have been built on wetlands. Mangrove areas in coastal areas have been drained. Even Mexico City was built on a lake. They've drained it. It's now a city. And I'm sure there's many examples in Brazil where natural wetlands have been destroyed. But the thing is, wetlands are really like we call the kidneys of the earth. And as we know from the Amazon, they purify water, they store water. They're a huge biodiversity. And yet we have come in and destroyed them. However, we still know that these wetlands perform many functions. So if we can mimic these wetland systems by constructing them, we can get wetlands on a smaller scale to perform these same values of water purification, water storage, biodiversity. Now, in the past in Australia, and I don't think we're alone, effluent from sewage was discharged directly into rivers, into lakes, into the ocean. And of course, that can cause pollution. But that water contains nutrients, and they also cause the pollution. But nutrients are also very important for agriculture. So why are we wasting water rich in nutrients by putting it into the ocean and lake? We would be much better off recycling that water and using it for irrigation on the land. So by discharging this water into lakes and ocean, not only are we wasting water, and remember Australia is a very dry country. We don't have as much rainfall as Brazil. We need that water. And we also need the nutrients, because also a lot of Australia, we're rich in minerals, yes, but it's a very old country and there's been a lot of weathering, and many of the nutrients have actually been lost from our soils. So in agriculture, we put a lot of phosphorus onto our soils. Phosphorus then runs off and into our rivers and creeks, and we get blooms of cyanobacteria. Where's the man doing research on cyanobacteria? on here. Okay. So as you can see, on the right-hand side, this was a golf course. Can you imagine they want to play golf in arid Australia? But we can recycle the sewage effluent after it's gone through the wetlands to remove some of the contaminants and make a nice green golf course, recycling the water. So just briefly, some of the issues then that relate to water and water reclamation and water reuse in Australia. Now, of course, there's our public realise that it's important that we need to conserve water. Water is a scarce resource in Australia. A lot of the time we have drought, though in the last 2 years we've had floods. So Australia, just like Brazil at the moment, is having climate changes of extremes. But drought is more common in Australia than flood. We also know wastewater contains potential contaminants that we're concerned about. We're concerned that the release of total suspended solids, organic matter, and nutrients can cause pollution. So we need to remove these to safeguard ecosystem health. We need to remove pathogens from wastewater to safeguard public health. And as mentioned earlier, nutrients and water are a resource. We shouldn't be wasting them. We should be reusing them. And we can reuse this water for agriculture, forestry, horticulture. As mentioned before, historically we have distributed our wastewater, our sewage, into oceans and rivers. Now we have to look at purifying that and recycling it onto the land. So overall, in Australia, every city, also our agricultural areas, are concerned with sustainable water management. And that's important. But society needs to recognise that in order to reclaim or reuse water, it must be affordable. We don't want to pay a lot for these processes. And of course, a lot of the time, the more traditional methods use up a lot of money. To build a large sewage treatment plant costs a lot of money. It costs a lot of money to operate it, so it's actually quite costly. In Australia, we also have some desalination plants for water, but it's very costly. And desalination uses a lot of electricity. So it is high energy cost, which is actually not good also for the environment because it uses up and produces a lot of carbon. And we want to make sure that water reclamation is going to result in good water quality that will safeguard our aquatic ecosystems, will safeguard human health, reduce energy use, minimise greenhouse gas emissions, minimise unwanted products, at the same time producing wastewater that's acceptable to the community. And what my research has shown is that wetlands can be a solution to some of these issues because they're sustainable, they're low cost, and we can still get good water quality from that. So what are constructed wetlands then? They include ponds, another one called bioretention systems. But the important thing about these engineered systems is that we make use of vegetation, we make use of the soil, and we make use of the microorganisms present in these systems to remove the contaminants. And we've been looking at these constructed wetlands now to treat both wastewater from sewage, but also stormwater in our cities. So from an engineering point of view, we recognise two basic designs of our constructed wetlands. The one on the left typically is open water, like a lake. However, we want to make sure that we maximise vegetation, therefore it must be shallow. Because with a lake, it's deep, and many plants can't grow in deep water. That needs to be shallow. But those sort of wetlands we call a surface flow wetland. And of course, because there's open water, we get much biodiversity in there. Different plants, different aquatic animals, including fish, and we can build up a wetland ecosystem. The other type of wetland is subsurface, and instead of being open water, it's actually filled with sand or gravel. So again, that can also be very important for maximising removal of some contaminants. But obviously it doesn't offer as good biodiversity because there is no open water for aquatic organisms. But we have found that the subsurface flow wetlands are good because we can improve removal of phosphorus and also nitrogen in these systems. So we're now finding a combination of both is important. So just remember these two basic types of design of engineered wetlands. So here are some examples then from Australia of wetlands. At the top, they're wetlands used to treat wastewater from sewage. And at the bottom, these are wetlands in the city, in Brisbane City, used to treat stormwater. These is example of the subsurface flow, and you can see the construction stage at the top, and that is then filled with gravel, and you can see the plants growing. So they're the subsurface flow wetlands. These are also subsurface flow wetlands in an urban area. We are using them along the middle of the streets where the freeways are, so that all the water when it rains, which contains heavy metals, oils, nitrogen, phosphorus, runs off the road into these subsurface flow or bioretention systems. And of course we can make them very attractive. So this is part of greening urban cities in Australia, including Brisbane, Melbourne, Sydney. And every new development now, housing development, all the water from the roads and the roofs has to pass through either a constructed wetland or one of these subsurface wetlands. And that's to get approval now for any new subdivision in Australia. And as I say, they can look attractive. At the same time, they are purifying water. As you can see, the design of wetlands incorporates these open water areas, which we call ponds or lagoons, and then these vegetated areas. And both are important for processes. I would just point out these conceptual designs at the top. Both of these areas are within the city of Brisbane, and originally they were a concrete channel. Now I haven't got a pointer, but that line through the middle represents the original concrete channel. This is what we call a retrofit system. We have created a concrete channel with no biodiversity into a beautiful wetland, which is this one here, underneath. Similarly, the one at the top, notice Peter, Bowie's flat. Okay, originally, again, you can't see as well, but there was, this is a big sediment basin. So all the stormwater first comes into a big sediment basin, which is quite deep. And then water from the sediment basin goes through this wetland and comes out the other end. But originally, all that was a concrete lined channel. So we have not only improved the overall aesthetics, and you can see the houses are right, the values of the houses improved because they were looking out onto a beautiful wetland. So water quality was improved. Also water storage, there was less flooding because the wetland stores the water, purifies the water, provides a habitat for frogs, insects, and has social value. It's aesthetically pleasing. People walk around. They take their dogs for walks. And again, in terms of economics, the value of those houses has improved too. So that's when I say these are important, ecologically, socially, and economically. And this is in downtown Brisbane. Very briefly, we can change a concrete channel to look something like that. And that's what we've done. Okay? Now remember too, we are also constructing similar wetlands to treat acid mine drainage. And even with a pH of 3, we have found many plants, many aquatic organisms, even fish will survive with pH 3. So we can, again, incorporate that, maybe part of the rehabilitation process. Let's create a wetland in that area. So here we are, myself and other colleagues, going out into the wetlands to assess the biodiversity in those wetland systems. So big ecological value. I thought I would just put in this slide because I know people in Brazil are concerned with mosquitoes, and I think is it dengue fever that can be a problem. But if we have a wetland, all of these animals found in the wetland, we call them macroinvertebrates, they all eat mosquito larvae. So wetlands are not a problem for mosquitoes. More of a problem is old tyres, containers. That's where the mosquitoes are breeding. Mosquitoes are not breeding in wetlands. And this is one of the issues I've had to convince the community. Because sometimes the community, oh, wetlands, mosquitoes. No, we don't want wetlands. So we've done research, and I've published this, so if you want to check my name later, I've got this all published about how in the wetlands we don't get mosquitoes because these are natural predators of the mosquitoes. All right, I'm now going to just briefly talk about water treatment processes. And as I mentioned, in our design, we often have wetlands and ponds. And by wetlands, I'm talking about areas with shallow areas with lots of dense vegetation, whereas ponds are open water areas. And any of us that have had any experience with wastewater treatment know that we can talk about physical processes, biological processes, and chemical processes. So a typical sewage treatment plant has physical, biological and chemical processes. So do our wetlands and ponds. They also have physical processes for filtering out the sediment and the organic matter. They have biological processes for removing the nutrients either by the plants or the microorganisms, and then we can have chemical processes. Phosphorus, for example, can be adsorbed chemically if we have appropriate media that maybe has iron or aluminum as part of it. And also we get UV disinfection from sunlight, which can help to remove pathogens as well. So just following on then on some of these removal processes in constructed wetlands, I'll go through this quite quickly now, but essentially suspended solids and organic matter, BOD, are removed by, as I say, mainly physical processes. Nutrients are mainly removed by biological processes, but we can get some chemical adsorption. These are some of my experiments. These are my little mini wetlands, but these are the subsurface flow wetlands. And as you can see, that's all the gravel. And on the right-hand side, you can see the roots of the plants have gone all the way down into the gravel to the base. But that's good because the roots remove the nutrients, they remove heavy metals, and of course, we can have different sorts of plants growing in these areas. And these have been also used in urban areas. And again, we found that if we want to improve phosphorus removal, we combine bauxite. Do you have bauxite here? Yeah. The byproduct of bauxite, which is a red mud. We put 5% red mud with 95% sand, very good for removing phosphorus. So if you want to get rid of a lot of phosphorus, because normally wastewater treatment does not get rid of much phosphorus, but you put 5% red mud residual with 95% sand, we get 99% removal of phosphorus. So again, that's a very good application of a mining byproduct to mix it with sand to remove phosphorus.
So 95%
sand and 5% red mud residual. So it's the byproduct. Also too, we find that plants can vary in their ability to remove contaminants. So plants can have luxury uptake for phosphorus. Plants can also have luxury uptake for different contaminants, arsenic we were talking about, copper, and we call these plants hyperaccumulators. So we can actually design our wetland to maximise removal of, say, phosphorus or metals by selectively choosing different types of plants. As I mentioned here, phosphorus absorption is important, and we can increase phosphorus absorption by adding this 5% red mud. We also have in Australia krasnozen soils. Who's soil person? Do you know krasnozens? They're a derivative of volcanic basalt. Krasnozens we call them, but it's red. It's a red colour. Once again, it's high in iron, so very good for phosphorus absorption. And again, we've mixed 20% of the krasnozem soil, 80% sand, and get excellent phosphorus removal. Another thing we've used too is what we call water treatment residuals. Now that is a byproduct of water treatment, not wastewater, but water treatment. Because at least in Australia, and I'm sure it's similar here, before we get to drink the water that comes out the taps, they add certain chemicals to make sure a lot of the particles precipitate out of solution. And then, of course, they chlorinate it. Now, the particles that precipitate out of solution form what we call a sludge. The sludge is then removed and dried. Now, in Australia, that sludge then has to be disposed of. So again, it's a waste product. However, we have found that by combining this waste product with sand, that we now remove excellent phosphorus. So again, it's a reuse of a waste product. But of course, that is really only applicable with the subsurface flow wetlands. So we're finding quite a few applications of reusing byproducts or waste products, which is a good application. Now, pathogen removal, because it's not only nutrients and suspended solids that we want to remove from wastewater and stormwater. We also want to remove potential pathogens. Well, wetlands are very good as well because we have physical, chemical and biological mechanisms. But despite wetlands being very good at removing pathogens, in Australia it is still law that we must disinfect by chlorination or UV disinfection. And they are costly processes. So again, it's still a case of trying to convince the public and authorities that the wetlands do just as good a job. All right, so then I'm now on to the last section about the design. How can we design our wetlands for best performance? So we want nice, dense, vegetated zones to assist in filtering and sedimentation of our suspended solids. In free water systems, we find a combination of open water and dense vegetated zones with a variety of plants will maximise performance efficiency. And again, as I mentioned before, in subsurface flow wetlands, we have found different what we call media amendments that we can add to sand to maximise phosphorus removal. So plants, microorganisms and media amendments can give us very, very good performance in our wetlands. Similarly, for pathogen removal, the dense vegetation, but this time also open water, because UV light will automatically kill off a lot of those pathogens. Also in the wetlands, we find microorganisms that eat other microorganisms. And so we find that a lot of the potential pathogens get destroyed by existing natural populations of microorganisms in the wetland system. So really they don't survive at all. So what we've found here and then in terms of maximising our wetlands is maybe first of all have open water lagoon for disinfection, for physical filtration, to get rid of a lot of the coarse material and the sediment. Then we pass it through either a series of surface flow wetlands and then one of those gravel-filled subsurface flow wetlands, and we're getting very, very good removal of contaminants, or again alternating with a marsh and open water, a marsh and open water. And this is what we tend to have more maybe in our urban stormwater areas, this system, whereas in the top system maybe more for municipal wastewater. All right, so last two slides about overall values of constructed wetlands. Okay, so as mentioned, removal of contaminants provide a habitat for aquatic organisms, increased biodiversity. Wetlands being plants are solar power driven, doesn't cost anything because the plants rely on sunlight. So wetlands are solar power driven systems, that's what I call them. Also, and this is very important now in Australia, is carbon sequestration. I don't know about in Mexico, but in Australia now we're really big on minimising our carbon footprint. We're very concerned about carbon credits, carbon emissions, but wetlands sequester carbon. They remove carbon from the atmosphere. And I've calculated that my plants in the wetlands can accumulate as much as 3 kilograms of carbon per metre square per year. So not only are these plants removing nitrogen and phosphorus and suspended solids, they are also sequestering carbon. So that's a very positive aspect. In some instances, wetland plants can be harvested and digested to produce biogas. For example, the water hyacinth Icornia, which I know you have here in Brazil, and it can be a bit of a pest. In Australia, it's a weed. In Australia, we cannot use Icornia because it's a pest. But it does do a good job at removing pollutants. But it needs to be harvested, and that's maintenance. But if you harvest it, you have to do something with it. So at least if you can get biogas out of it, that's important. And as I said, we can use waste products to add to our sand to enhance phosphorus removal. And if we're using these waste products, that's also a cost effectiveness. It's environmentally friendly because we're using waste products to improve the performance of our wetland system. As I said, the wetlands remove pathogens. That means we could save money by not having to chlorinate or pass through UV disinfection processes. Again, our treated water can be used for irrigation, it can be used for rehabilitation, it can be used for restoration of new wetlands. In urban areas, these ponds can be used to store the water, and then that water can be harvested for irrigation of parks and gardens during times of drought. And again, as you saw from the earlier diagrams, in the urban environment, they can increase the overall aesthetics. They look attractive and people can use them for walking, and they're also good for community education. And I think that is the last. And this just shows some of the wildlife that we can get in our wetlands. All right, so thank you.